A uniform solid disk is mounted on an axle in such a way that it's free to rotate about a horizontal axis. The radius of the disk is 0.45 meters, and its mass is 26.5 kilograms. Alright, there's our mass. Let's see, our radius here is 0.45 meters. Alright, now there's going to be two forces applied to the disk. F1 is smaller than F2. So we do expect, just based on the symmetry, that this disk will want to angularly accelerate this way, clockwise. Angular acceleration. We want to determine what is the magnitude and direction of the net torque, and what is the magnitude of angular acceleration of the disk. Alright, so to get the net torque, we'll just want to sum up all the torques that are being applied. There's actually going to be just two in this case, T1 plus T2. And so we could do our net torque in relation to the z-axis. And what do I mean when I say that? I mean that up is positive y, to the right is positive x, and the z-axis actually points out of the page. One convention is make a circle with a dot, and that just means that the positive z-axis points at you. It's supposed to be like the head of an arrow. So like if you had an arrow with a pointed tip, and let's say it had feathers on it, let's say 4 feathers that maybe looked like this. That's the arrow. So the circle with a dot part is this, the front. And then in the back we actually use an X to represent the feathers. Like if you want something to point into the page. So that means into the page. And this means out of the page. But you can always set up a three-dimensional coordinate system using the right-hand rule, where the conventions are that you've got an x and a y in the normal math orientation, and then the z would point perpendicularly to both of them. So the way the right-hand rule is used for that is the pointer points in the x direction, the middle points in the y direction, and then these other fingers just do whatever. And so we have positive x with your pointer, and then we have positive y is the middle, and then the thumb points in the positive z direction. So you can always use your right hand to figure out what the right direction for z is. And in this typical math orientation, it's going to end up being out of the page. Alright, so when we do a torque relative to z-axis, we mean that the torques are either going to be negative or positive depending on whether they're into the page or out of the page. Alright, so one option for this disk then is to use another right hand rule called the corkscrew rule. And how does that work? Well, F1 alone would make your disc want to spin counterclockwise. So you curl your fingers in the direction of the force, and you make like a fist. Alright, it goes like this. And then the fingers curl around like that. Okay, this is called the right hand corkscrew rule. Now, the fingers represent the way that your object is twisting. Alright, so these would be like the forces on the particles. But the thumb represents the torque. But it's a pseudo-vector. Shows like an axis of rotation. The torque would be coming out of the page for this force, F1. So we want to make it positive. Positive torque. Whereas for F2, it would be the opposite. Alright, so let's show F2 real quick. Yeah, okay. So for F2, that's up here. So you gotta totally switch your hand around, so that you now have your fingers curling this way. But then your thumb points back in space when you do that. Alright, so F2 makes our disc want to spin clockwise. And now our torque pseudo-vector, this is the torque due to F2, whereas the one above was due to F1. Alright, so that's going to be a negative torque. It points like this, into the page. So this one's out of page. This one's into the page. Alright, so this will be T1, and this is T2. Now we can give unit vectors as well if we want. We don't have to. Like we could just say T1Z plus T2Z. In that case, no unit vector is needed. So I'll show what it looks like with the unit vectors in a second, but first let's just multiply R1 times F1, and here we'll have R2 times F2, but one of these needs to be negative. This one needs to be negative, because we said, according to our analysis, T2 points into the page, which is considered negative, because it's clockwise. And this one's counterclockwise. Alright, hope that makes sense. I'm going to move this down to here. The net torque will then be, let's see, R is 0.45. The force F1 is going to be 92.5. Then we need 0.45 times 115. So our net then, negative 10.13. Alright, not surprisingly, the final result came out negative, which means this disk is going to ultimately want to spin clockwise, because the force 2 just like wins versus force 1. So we could write it with unit vectors if we want as well. So the way we would do that is to use k hat or negative k hat. K hat is out of the page, and negative k hat's into the page. So that first one was a positive torque. The torque pointed out of the page. And so that's going to be considered the positive k hat direction. Whereas the F2 torque ended up pointing into the page, and that's going to be the negative k hat direction. So you can just assign those unit vectors to show the direction. So that's what it means if you see that. So negative 10.13 Newton meters k hat. Alright. Finally, we'll find the magnitude of angular acceleration. So we should use Newton's second law for that. Newton's second law for rotation. So that's going to be torque net equals I times alpha. Now this is a disk. So what we're going to want then is the formula 1/2 mr squared. Yeah, that's the formula for a disk. So we'll do net torque (1/2). Our mass is 26.5. Our R is 0.45. We have to square that though. Then we can solve for the alpha. So alpha is, I'm getting negative 3.77 radians per second squared. It'd be 10.13 for the magnitude. Clockwise tells the direction, and this one positive as well because they want the magnitude.